In this video, we are going to take a look at the more examples of the geometric series test, because we are going to keep coming back to this geometric series test as it's a really nice test for telling if a series converges or diverges, and it's one we know a lot of information about, like we know what it converges to. So we want to practice with this, and we will take a look at several examples. Big things we're looking for is we're looking for a ratio and making sure that absolute value of the ratio is less than 1. And we're looking for an A. And up here is telling us what we want our sequence to be written as. If our lower bound is n equals 1, we want to see an r to the n minus 1. And if our lower bound is 0, we want to see an r to the n. But we can find A by plugging the lower bound into the sequence. So we'll see examples of that. And then the r is just going to be the thing that has exponents on it. So we will take a look at some examples using this rule. So first example is this example, n equals 1 to infinity of 1/5 to the n. Pretty clearly, our r is going to equal 1/5. So just going to say right off the bat converges by the geometric series test because the absolute value of r is equal to 1/5, which is less than 1. However, what does it converge to? Couple ways we can think about this. Number one, we know anything is going to converge to a over 1 minus r. We know our r, that's 1/5. But what is a? And a, I said, first could be found by rewriting this series to look if we have a lower bound of n equals 1. So I want my exponent to be n minus 1. The way I make my exponent n minus 1 is to factor out a 1/5. And now we're in that form to say, hey, there is a. A is 1/5. Or to find a, we can the lower bound into 1/5 to the n. So a equals 1/5 to the first, which is 1/5. So either the rewriting of the sequence or the plugging the lower bound in gave us the same result. A is 1/5. R is also 1/5. So 1/5 over 1 minus 1/5 is 1/5 over 4/5, or 1/4. So this series converges, and it converges to 1/4. Second example, we don't have our series written out, but we're going to walk through how to find said series. So we know a series is a sum of a sequence, so we want to somehow write this sequence in a way that I can see a ratio that is being multiplied over and over. So rewriting this sequence, the series, we have 9/10, just reading those off and writing them as fractions, plus 9 100ths, plus 9 1,000ths, plus 9/10,000ths, and we would go on. All of these have a 9 in them, so I'm going to pull that 9 all the way out. And then I'd have 1/10 plus 1/100th plus 1/1000th plus 1/10,000th, and so on. These are all powers of 10, or powers of 1/10. So this really equals 9 times 1/10 plus 1/10 squared plus 1/10 cubed plus 1/10 to the 4th, and so on. And there we can generally see our R, it's 1/10. I'm multiplying by 1/10 every time. I want to start when I am actually using 1/10. So we would have n equals 1 to infinity times 9. And there is our series. We already identified R equals 1/10. A equals the first term of this. So we could either plug 1 in and see 9 times 1/10 is 9/10, or we already had the first term of our sequence in our series. That is 9/10. So this series, which is the sum n equals 1 to infinity, 9 times 1/10 to the n, converges by the geometric series test to, first, because the absolute value of R is equal to 1/10, which is less than 1. And it converges to A over 1 minus R, which is 9/10 over 1 minus 9/10. Sorry, 1 minus 1/10, which is 9/10 over 9/10, which is 1. So this is a cool proof that 0.9 repeating, even though there's always a little bit where we're not quite at 1, it is actually true that 0.9 repeating is equal completely to 1. Next example, we have another example where we don't have the sequence yet, but with a little bit of work, we can find that out. First, we know that A, our starting term, is -2. So if I do an n equals 0 to infinity of -2 times whatever I'm multiplying by to the n, I will have my series. Second thing is figuring out what am I multiplying by. And it's easiest to see here, but we can check it with the others. So when I move from -9/2 to a positive 27/4, I am multiplying by 3/2. So and it's a -3/2. So multiplied by -3/2. Does that work for these others? To go from 3 to -9/2, that is multiplying by -3/2. To go from -2 to a positive 3, yes. -2 times -3/2 is positive 3. So our R is -3/2. So A equals -2, R equals -3. So the first thing is, does the series converge or diverge? And actually the series n equals 0 to infinity of -2 times -3/2 to the n diverges by the geometric series test because the absolute value of r, which is equal to the absolute value of -3/2, is greater than 1. So this series actually diverges, so there is no value we're finding it to diverge to. Next example. I'm going to use this example to show what we're looking for and how we can keep rewriting, but it's actually a little bit easier to recognize that I'm going to plug my lower bound in. So a sub 1 equals 3 to the n minus 1, 3 to the 1 minus 1 over -5 to the 1 plus 1. 3 to the 0 is 1. -5 squared is 25. So a sub 1 is 25. 1 over 25. R is the stuff with the exponents. So that is the 3 because it has an exponent, and that is the -5 because it has an exponent. So R is -3/5. Now, quickly using the rewrite method to show this is true as well. Since I have a lower bound of n equals 1, I want to rewrite this so that everything has an exponent of n minus 1. Well, 3 has the exponent of n minus 1 already, so that's going to remain unchanged. So we have 3 to the n minus 1. But -5 to the n plus 1, I want it to be -5 to the n minus 1. That is 2 less than what I originally have. So I actually took out a -5 squared, right? 2 plus n minus 1 is n plus 1. Meaning there is our series rewritten. And if we rewrite this a little bit more, putting everything with that exponent together would be 3 over -5 or -3/5 to the n minus 1. And everything out without the n minus 1 exponent would be 1 over 25. And there is A and there is R, just like we just found. So R is -3/5. So the absolute value of R is less than 1. So the series n equals 1 to infinity of 3 to the n minus 1 over -5 to the n plus 1 converges to 1/25 over 1 plus 3/5, because in the formula, the sign on R does matter. The formula is 1 minus R. R is negative, so it's 1 plus R. 1 over 25 plus 1 over 3/5. 1 plus 3/5 is 1/25 over 8/5, which works out to be 1/40. So it converges to 1/40 by the geometric series test. If you're noticing at the end of these, there's always this conclusion sentence. And as we add more tests, these conclusion sentences are going to become more and more important. But the conclusion sentences we need is a series converges by some test and the reasoning with that test. So series converges, diverges by test with reasoning. For geometric series, we know what they converge to, so we include that information. But as we add more tests, these sentences is series converge/diverge by test because reasoning. And sometimes the because reasoning is inside your work, but we need to make sure we see the reasons clearly listed out. And so our last example for these geometric series tests, not going to rewrite it at all, just going to use the quick method of the thing with the exponents is only the 3/10. So R is 3/10. Don't need to worry about any other values because those are the things with the exponents of n. A is when I plug in the lower bound to that sequence. So plugging in the lower bound to the sequence, I'd have 6 times 3 to the 0 minus 2 over 5 times 10 to the 0 plus 1. This is 6 times 3 to the negative 2 times 5 over 5 times 10. 3 to the negative 2 is over 9 times 5 times 10. 6 and 9 cancel to be 2 and 3. 3 times 5 times 10 is 150. And the numerator is 2. So A is 2 over 150. Meaning, because the absolute value of R is less than, well, is equal to 3/10, which is less than 1. The series n equals 0 to infinity of 6 times 3 to the n minus 2 over 5 times 10 to the n plus 1 converges. There's our, does it converge or diverge? Why does it converge or diverge? It's by the geometric series test. Because we already have that reason stated, because R is 3/10, which is less than 1. And it converges to A, 2 over 150, over 1 minus 3/10. Which all of this ends up working out to be 2 over 105. So there are our examples for the geometric series test.